Ladies and gentlemen, in this gaming.com video, we have yet more on asynchronous compute and the Nvidia fiasco. So you might recall just a couple of days ago that Oxide Games did point out that, the reason that AMD have these performance advantages with Ashes of the Singularity is due to asynchronous compute, and that their title does use asynchronous compute. Not heavily, it's certainly not, the poster boy for asynchronous compute usage, but it does utilize it. However, while there was a lot of information saying that Nvidia's cards could not do that, and that, basically there was a lot of stuff that was being reported, and it was all up in the air. But now a developer has once again issued some comments, and I'll read them out pretty much verbatim. Maybe adding a little bit of English into it, but regarding, he says, as he said, I'm going to add English into it, and immediately screws up, so that's a great start. Regarding asynchronous compute, a couple of points on this. First, though we are the first DirectX 12 title, I wouldn't hold us as the prime example of this feature. There are probably better demonstrations of it. This is a pretty complex topic, and to fully understand it, it will require a significant understanding of the particular GPU in question that only an IHV can provide. I wouldn't certainly hold Ashes up as the premier example of this feature. Now, this is the cool part, well, the exciting part, or the telling part. Anyway, we actually just chatted with Nvidia about asynchronous compute. Indeed, the driver hasn't fully implemented it yet, but it appeared like it was. We are closely working with them to fully implement asynchronous compute, and once again, obviously, I'll keep everyone posted as we learn more. So, what we know about the Nvidia fiasco right now is that AMD is stating that Nvidia can't handle asynchronous compute, at least in the traditional sense, while Nvidia are being a little cagier. But this does come down to some context switching. Now, I have discussed context switching previously rather in depth with the Xbox One SDK developer breakdown. So if you're unsure about context switching, you could go to redgamingtech.com, search for context switching, it will pop up, or you could search for it on this YouTube channel. I don't want to spend too much time going into it because I'm trying to keep this fairly short and snappy. I do want to do a breakdown of all of this stuff once it becomes clearer, but what I don't want to do is do a whole analysis and then it turns out that it's not true, because we seem to be getting new details of this every day or two. So anyway, back to the whole situation. So whether this can be done through preemption and context switch is unknown. So the problem with context switching and preemption is that you're going to be adding latency to this. And speaking of context switching and latency, someone has actually been talking about this, tech reports David Cantor, and he believes he was speaking to someone at Oculus, and he said, and I quote, "I've been told by the folks at Oculus that preemption context switching is prior to the Skylake 8 generation, which had better preemption, but the best preemption context switching was by AMD by far." He says Intel were pretty good, but Nvidia was possibly catastrophic. Real issue is if you have a shader running, a graphics shader, and you need to let it finish, and that could take a long time. It could take you over 16 ms. Now, for a little bit of example, that basically means that if you're running, say, a graphic shader, if you're having it draw something and then you need it to go to compute-orientated tasks, you're pretty boned. You have to basically switch the context, have it finish one thing, then basically have it switch to the compute task and then back. It's not able to do both things at once. The problem is, because of that, you start to deal with time-sensitive natures. Effectively, graphics are all about time. We've heard a lot about this recently with multi-compute, with multiple GPUs, with it's just constant. It's all about bubbles of time. It's all about how long a specific task and operation, whether it's compute, whether it's even doing something like defragging the memory, whether it's getting a a bunch of information of, hey, what does this do, what does that do, whether it's pulling something from memory into video memory, whether it's something simple like artificial intelligence, well, not simple, but whether it's something like artificial intelligence, whether it's physics. All of this stuff has a time factor. It costs a certain amount of time for either the CPU, the GPU to process a piece of data. In some cases, it can be that you have consider it to be a control thread, I guess, which is issuing instructions to other threads saying, I need you to process this. So let's say you've got a 4-core CPU, let's just make it simple. We'll call it A, B, C, and D. So core A will be the control, core B, C, and D, that would be the other 3, would be the worker threads. What you might have, and this is a very simplified example, but you might have thread A, which is basically telling the other thread, it's basically figuring out what needs to be processed and when, and basically keeping I guess you could say like an overwatch, an eye on what's going on. And the other 3 threads would be the worker threads. They're actually calculating game logic or processing data to send to the GPU, because remember, the GPU needs to actually receive instructions. Those would be the draw calls or batches, which is obviously whole bunches of data, and all of that stuff is being sent in real time. Unfortunately, once again, all of this does come at time intervals, and so a millisecond, once again, a very simple way to calculate this if you're ever that super bored do you want to kind of start messing around. I'm literally just pulling up a calculator for the lulz, but if you type in 1000, which represents 1000 milliseconds, which represents 1 second, and then you divide that by, let's for lulz say 60, which is obviously a frame rate of 60 frames per second, you get 16.6, which means that if you want to maintain 60 FPS, all of the game logic, all of the stuff, all of the workload in that particular frame must be completed within 16.6 ms, roughly, as an average. Obviously, if you're targeting a higher frame rate, for example 90 or 120, what have you, then you could start doing the mathematics. If you're targeting 30, on the other hand, which is what a lot of consoles go for, then it's 33 ms. In other words, you've got that extra time, and that's all it is. You're basically giving the hardware that a little bit more additional time, which, anyway, you get the idea. Now, we are going to discuss another point with actually the Singularity regarding CPU load balancing and also DirectX 12. So, load balancing is real simple. In a nutshell, it's how does data get distributed over the CPU cores. So the more CPU cores you've got, it's actually quite hard to feed the beast. Effectively, what you need is effective and efficient code, and to utilize as many cores as possible. Back when multi-threading was becoming a thing, this is back when, let's say, you had the early Athlon processors. No, not the T-breads, but we're referring to like the X2s, like the X2 3800s, the 939s, those type of ones. Or even if you want to go a little bit Intel with this, and you want to discuss like hyperthreading with the Pentium 4 hyperthreadings, the good old Pentium 4 3.06 GHz hyperthreading. Anywho, back then, there were some applications certainly which did utilize multi-threading. Obviously, one of those would be something like Adobe Premiere, and obviously a lot of virtual machines, all of that stuff. Pretty much anything creative, video editing, some programming, compiling, they'll all use it. 3D rendering as well, but the average game and a lot of Windows applications, they just didn't. You had the odd outlier, for example, I believe pretty much any game in the Quake 3 engine. Don't quote me on that, but I believe pretty much any. I believe quite a few in the Unreal Engine. They were able to support multi-threading. It doesn't mean that they were able to spread logic equally, and that means that, let's say you had 2 cores, the other core necessarily wouldn't be able to send, say, draw data to the GPU, but it would be able to do other things, for example, just for the sake of argument, basic game logic. So in the case of actually the Singularity, and indeed Direct3D12 in general, it's not down to the driver or / API to actually handle load distribution. So to actually get a CPU to 90% load on an 8-core machine, Oxide are actually pretty happy. They're actually saying that, you know, it's actually really nice. Additionally, hitches and stalls are largely an application's responsibility under Direct3D12. In Direct3D12, essentially everything that could cause a stall has been removed from the API. For example, pipeline objects are designed so that the dreaded shader recompile won't ever have to happen. We also have precise control over the graphics command is queued up. This is important for VR applications. Also keep in mind that memory models for D3D12 are completely different. At an OS level, I'm not sure you can honestly compare things like memory load against one another. In Direct3D12 you have more control over residency, and we may, for example, intentionally keep something unused resident so there's no chance for micro stutter. If that resource is needed, there is no reliable way to do that in Direct3D11. Thus, comparing memory residency between two APIs may not be meaningful, at least until everyone's had a chance to really tune things for the new paradigm. This is really important stuff, actually, because for those who aren't too familiar with it, the basic premise is Direct3D12 or DX12 or whatever the hell you want to call it. In fact, we could also leverage this for Mantle and Vulkan as well, which are obviously two competing APIs. The whole purpose is that memory management and pretty much anything actually is much more down to the developers. So if you decide to leverage DirectX 12 code paths, obviously DirectX 11 is still there. So let's say that, you know, you're making Limbo 2, and I don't know why I keep using bloody Limbo as an example. I guess it's because it's an aesthetically pleasing game. It's fairly simple, it's not particularly taxing. You could basically run it on a gerbil hamster-powered PC. But regardless, you know, if you're making something like that, you don't need to worry about optimization necessarily. You don't probably give a crap whether you're running it across 1 core or 50 cores. It really won't make that much of a difference. It's not particularly time sensitive in terms of frame rate, it's not particularly latency sensitive, and it's certainly not really graphically sensitive. I mean, the thing's basically black and white, for goodness sake. But anywho, the point being, on games like that, you don't need that level of complexity, but for games which do, you basically have to control things, and as Microsoft themselves have pointed out numerous times on numerous occasions on their various presentations, and we have done multiple DirectX 12 breakdowns and analysis. You can search for those like DX12 GDC or even Build Conference. We've done tons of them which go through all of this stuff in quite painstaking detail. And you know what it is? It's like DirectX 12 puts a lot more responsibility to the developer, and in a way that could be a good thing. It also means that it kind of scares me, because if you've got a really bad developer, or one who's not too familiar with it and they're just going that path anyway to say the game's Direct3D12, I have a feeling there's going to be quite a few day one patches. Let's go with that. Day one patches galore. Essentially, it's really down to you to manage the memory. So for example, you need to say, hey, you know what, I don't want this texture, I don't want this asset in memory anymore, it's not going to do me any good, you know. That texture, that asset, that object was for a bush that was, you know, in the desert back there, and now we're in this city and there's no bushes of that variety. Obviously I'm just making examples out the top of my head because I've been playing a lot of Metal Gear Solid today. Anyway, I think that's enough of that subject. I will quickly close out. I have been playing an awful lot of Metal Gear Solid, as I mentioned earlier, and it's a pretty damn good game. I'm going to be doing like a reviewy thing of it, not a first impressions thing. I've actually played quite considerable amounts, so I'll probably do a succinct review. I've done most of the principal photography and videoing, if that made any sense, of the SSD review, which is a Kingston one, which they sent us a review, so that should be up tomorrow, which is Sunday or Monday, depending. It's going to be a bit lengthier because they've also sent the external caddy, which you can basically use to plug into a USB 3 port. So I need to do some testing across a couple of different PCs for that. And it's also my first SSD review. So the problem with first reviews is that you have to kind of think, okay, what applications do you use? What's the best way of doing it? And then you screw up, and then you have to redo it all over again. It's not as difficult as I'm probably gonna eat these words in like 2 days time, and I'm probably gonna be like, I'm really, really sorry. But it's generally, I think GPU reviews are probably about the trickiest, because you A, have to go through all the different settings, B, you've got driver revisions to worry about, and C, it can be a bit of a pain in the butt to compile all of the different different benchmarks. So hopefully SSD probably won't be as difficult. We've got some memory as well to review, which is DDR4, 16GB. That's a whole memory kit. That I don't know when it's going to be reviewed. I'm still on the fence between Skylake and 5820K. Obviously Skylake, it would be a 6700K, so I'm not sure which one I'm going to go with yet. So anyway, hopefully you've enjoyed the video and found it somewhat informative-y. I'm going to be doing a few more of these lengthier, kind of rambly, techie, bloggy things. I don't know if that made any sense, but in my head it made sense, and I started to speak out loud and it went really badly. Anywho, I'm going to be doing more of those again, because I used to do quite a few and people seem to like them. I guess people just kind of like droning out, and maybe falling to sleep to my sexy English voice, I'm not sure which. Yeah. Now I've scared you all, I'm going to leave you to it. There are going to be a few extra additional changes to the channel. We've got a couple of new things, for example the review thing that I mentioned, which should be debuting with Metal Gear Solid 5. As I said, really enjoying the game so far. I'm not super far into it, and I'm not going to mention any spoilers, but I'm like, I don't know, 4 hours in, and I've been recording every last minute of it, so it should be kind of a pertinent review if nothing else. And I'm also going to be eventually recording a couple of other reviews as well. Hopefully you can get the Metal Gear Solid 5 graphics comparison up as a bit of a prelude, or a bit of a spoiler, I guess you could say. The PC version looks rather pretty. I haven't done any benching or anything like that, but I'm hoping to test it out on a lower spec rig as well. What I'm kind of thinking is maybe try it on like a GTX 960 or maybe a 760 or something along those lines, but on an R9 390, which just happens to be the GPU we use in our rig. At the moment, we actually have multiple GPUs as regular viewers know, and sometimes we just switch between AMD and Nvidia just for the hell of it. But at the moment, the game just runs absolutely beautifully with all settings at absolute max. It's really quite impressive. Anyway, I'm going to get going. Hopefully you've enjoyed the video. I'll see you soon. Take care. Bye for now.